Well, I'm very happy to be here. It's been quite a few years since I've been in math science, and the profile of the faculty has changed, of course. But still, there's many old friends and many new friends like Arnav, etc. I've sort of prepared this mini course at a MSc, advanced MSc level. Okay, so I'm going to sort of request the pardon of those who are much beyond that level. And even if you students, you feel that somehow it's going too slow, etc., you please accelerate me, basically. Okay, so I'm sort of going to give it at the level of an advanced MSc student, basically. And the subject of the talk, the subject of these lectures, is the kinetics of phase transitions. So that's where we're going to start with. Okay, let's get some chalk out here. So I'm going to talk about the kinetics of phase transitions. I hope my writing is not as good as it was never too good anyway, but it's even worse now. I hope it's readable, huh? ठीक है, हाँ, okay. By the way, particularly for the students, just interrupt me if you have any doubts. I mean, I don't want to. I mean, there's no prescribed syllabus to be covered or anything. I'd rather that what we cover is done crystal clear to you guys. Okay, there will be a lot of new concepts, I think, but I'll try to sort of introduce them at a rather sort of basic level. So what is the kinetics of phase transitions? Well, the kinetics of phase transitions is, I mean, you know, phase transitions are universal in nature. And of course, very early we encounter this first example of phase transition where you realize that water exists in three phases, or at least three phases, I should say. And of course, you see this in your class 10 textbook already. You have liquid phase, you have a water vapor phase, and you have a solid phase, as a matter of fact. Actually, water, by the way, is still an open statistical physics problem. We now know that it has some 25 plus phases, and it's really a very remarkable kind of scientific system. But that's besides the point. So one now has, I should say, a reasonable understanding of the equilibrium aspects of these phase diagrams. Okay, and that's sort of the generic statement I want to make. As a matter of fact, the last 50 years of StatMech, one of the greatest developments has been the development of the renormalization group, which we've used to understand what happens around the critical point. Okay, so that's something I presume you study in your StatMech courses, and if not, you should sort of insist on learning learning the techniques of RG, basically. Okay, but I'm not interested in static aspects of the phase diagram. I'm going to ask about kinetic phase transitions, and that's the following kind of problem. You take a tray of ice in the freezer, you put it on the table. Now it's at room temperature, it would like to melt, right? And what is the process whereby the unstable ice phase melts into the preferred liquid phase? Okay, so this seems like a very simple kind of problem, but you'll find that though I use a certain language, these are paradigms for a whole host of physical phenomena in nature. Let me give you another example from your daily life. You have a cloud, it consists of supersaturated vapor. How does the supersaturated vapor will like to be liquid, but how does it undergo that dynamics of converting from the supersaturated phase to the preferred equilibrium phase? Okay, again, that's a kinetics kind of problem. Okay, so that's the sort of problems we're going to look at, and though I'll use, as I said, certain terminologies, oil and water, ferromagnet, etc., I'll try to point out that these ideas are very universal, and we now have a sort of understanding at a universal level, which at least I hope to share part of with you. And this understanding is about as broad and generic as the understanding we've gained of equilibrium phase transition. So that's the development of the last 20, 30 years. I've had some involvement in this development, and let me sort of try to share my understanding of it. As I said, I'm going to do it at a very pedagogical level, or I'll try to be pedagogical. but if there are any doubts, you just stop me. Okay. So let's start off with an introduction. So our starting point in StatMech is almost always the Ising model. So the Ising model, I think you've all seen multiple times. You basically have a bunch of atomic spins sitting on sides of a lattice. Let's say you label those as Si, sigma I or Si. In the simplest version of the Ising model, these take values plus or minus 1 or plus or minus h bar by 2. And the nearest neighbors are the only ones that are assumed to interact, because the wave function sort of is sort of localized on a particular site, and the exchange interaction makes the spins want to align. Okay, it doesn't matter whether they align positive or they align negative; it just wants to make them align. Okay, so that's sort of captured in this Hamiltonian, which is the well-known Ising model. Let me sort of make sure I use the same nomenclature as my notes, and that of course has a interaction term. That's the exchange interaction, and that indicates a sum over nearest neighbors, Si, Sj, and minus h summed over I, Si. So this is a magnetic field term, this is a one particle term, and we know how to deal with one particle terms. And this, of course, is what gives rise to the cooperative physics of the Ising model. It's a very beautiful physics already, and captures many of the main features of critical phenomena. Okay, so as you can see that if nearest neighbor spins are the same, either plus 1 or minus 1, that contributes a minus j. So it brings the energy down, and that's usually good, basically. Okay, I mean, this is nothing new out here, basically. I think this is all stuff that you've seen before. You can also have anti-ferromagnets where J is negative, but those are identical to ferromagnets. So let's just stick with the ferromagnet right now. So that's a model for a ferromagnet. You try to solve it, and this also you learned in your earliest StatMech classes, that this very simple idealized model of a ferromagnet is not solvable. Okay, you can solve it in one dimension. Ising already did it without a magnetic field, and then Kramers and Warnier did it later with magnetic field. There's a very beautiful transfer matrix technique, which I hope many of you have learned. And then in 2D, Sagar produced this absolutely brilliant solution, also inventing a lot of new mathematics in the process, where he solved the 2D Ising model without a magnetic field. With the magnetic field, it's still not solvable in 2D and higher dimensions. Okay, so that's sort of bleak in some sense, because that's, as I said, your elementary model of a ferromagnet, and that's not solvable, unfortunately, in general. Okay, nevertheless, as physicists, we sort of press on, and the usual sort of approximation you do is the is the mean field approximation. So let me tell you how it works. Let me say this in the context of the ferromagnet. I'm not going to work through the mean field calculation, because I presume you know that. Basically, the expectation value of the spin at a site k turns out to be the solution of a transcendental equation, tan hyperbolic beta j sum over the neighbors of Lk, SLk. Okay, that's the first term, and the second term is beta h Sk, beta h, basically. That's it. Yeah, just beta h. Okay, so that's the mean field solution of the Ising model, which I sort of, if you haven't seen it for a while, just sort of derive it again, or spend a few minutes deriving it. And that basically is also known as the Curie-Weiss equation, and basically it tells you that the magnetization is a function of this transcendental equation. So it's a little harder than a regular equation, but not much harder. In particular, if H is uniform, then Sk is just equal to a uniform magnetization. The system is translationally invariant, and that gives you the usual equation: m is equal to tanh q, where q is the coordination number, the number of nearest neighbors. It's 4 on a 2D cubic lattice. So Q beta J M plus beta H. Okay, so that's a more traditional form of the Curie-Weiss equation, which you normally encounter. Maybe I just sort of put that in a box, and you can solve that on a computer, or actually, and I worked this out in my StatMech class, you can actually solve it on the board in about a couple of lectures, and you get your first equilibrium phase diagram. So basically the phase diagram is the following. The experimentalist can adjust the temperature, she can adjust the magnetic field, and say she can adjust the number, but let's just keep the number as 1 mole of atomic spins. Okay. So what she sees is this following famous phase diagram. There's a critical point in here, and the critical point is labeled as TC, HC. HC by symmetry is just 0. That's a second order critical point. And then you have a line of first order phase transitions. Let me label those as 1. And you have an up phase and you have a down phase, basically. Everybody seen that phase diagram? Huh? Okay. And you can, of course, get a mean field estimate for TC. In the known exact cases, that's usually off. In 1D, it's a total disaster, but even in 2D, it's sort of about double the sort of Onsager solution estimate. Okay, so that's the phase diagram, and our understanding of this phase diagram has grown in leaps and bounds. In particular, the last 50 years of statistical physics has focused on what happens at the critical point. And at the critical point, maybe I should just say this because the physics is so beautiful, the correlation length of the system diverges to infinity. And the correlation length diverging to infinity means, see, the microscopic interactions are still nearest neighbor, cut off by a lattice. But the sort of physical length of the system diverges to infinity, which means that by adding up these nearest neighbor cooperative interactions, you see interactions out to a long distance, and you can actually do this experiment in your hostel rooms. You take a boiling liquid and just poke a needle in it somewhere, and at the critical point, the entire liquid will respond back to you. It's so cooperative that if you agitate one spin somewhere out here, at the critical point, the entire system sort of responds. So that's the collective behavior. Of course, in the modern context of active phenomena, which is a very sort of well-studied area right now, you have these bird flocks which are at a critical-like state. If one bird sees an obstacle and turns, even though presumably the birds just have nearest neighbor interactions, all the birds will turn, and so will if the fish sees some shark coming or some such thing, one fish sort of twists its direction, and the entire shoal of fish responds, etc., etc. So criticality is a very sort of beautiful phenomena, and going with it are names like universality. Universality is simply the statement that a lot of different systems show very similar behavior. Very similar behavior means, one should be clear on that. What very similar, I mean, obviously, if a fluid and a magnet show very similar behavior, you can't put a magnet in a glass and drink it up, right? That's not a sensible thing to do. They show similar behavior in the sense that various quantities at this physical point show power law behaviors in the distance from the critical point, and that those exponents are universal across vastly different systems, ranging from magnets to fluids to liquid crystals to the early universe and so on and so forth, basically. Okay, so you have universality, and these tools of the renormalization group have been essential in understanding this concept of universality. You also have this concept of irrelevance, which is sort of linked to universality. And irrelevance simply means that if somebody comes and tells you that this Ising model, actually there should be next nearest neighbor interactions and next nearest neighbor interactions and so on and so forth, because this is not a realistic model of a ferromagnet. The point is that many additional terms that you could add on are become irrelevant at the critical point, basically. Okay, so this is actually a pretty good paradigm for what's happening at the critical point, though perhaps not at various other places. Okay, so that's the static aspects of phase transitions. In these lecture series, I'm going to consider the following problem. I start off at time t equal to 0. So this is a non-equilibrium problem now. I start off at time t equal to 0 at t greater than Tc. So I'm in my disordered paramagnetic phase. All the spins are sort of randomly aligned. I rapidly quench the system below the critical temperature. I can quench it to 0 temperature, or I can quench it to sub temperature below the critical temperature, and then ask how this system evolves. So this is like my tray of ice. The paramagnetic phase has been rendered unstable by this quench, and now I have to evolve into my ferromagnetic phase. Because I'm sitting on this line, the system is equally happy for the spins to point up or point down. Okay, so the question is, how does it go from its disordered paramagnetic state to a new preferred equilibrium state? And this is a paradigm for many ordering processes which one encounters in nature. Okay, so again, as I said, I use the term ferromagnet, but it's a paradigm for sort of many different processes one encounters. Okay, so that's my first example of a kinetics of phase separation problem, which I will sort of try to discuss in some detail. And my second example is that of a binary alloy. Again, I'm not sort of going to go into the mean field derivation, but basically the binary alloy is also described by the Ising model. In the binary alloy or the binary mixture, each lattice site can have either an atom A or an atom B, right? Then that's it. That's a simple model of the binary alloy as you see in multiple books. Any two-state situation can be mapped into an Ising model. Again, the underlying physics is that A likes A, B likes B, and A dislikes B. Okay, you can have examples, rare examples of other things also, but that's a generic situation. Okay, so you have a Hamilton. So typically you model these by spin variables. Si, there's no actual spin, there's pseudo spin variables, and the spin variable plus 1 corresponds to A, minus 1 corresponds to B. If you go back to the Ising model, you see that the system is happiest when energetically happiest when nearest neighbors are A, either both A or both B, and it's unhappy if you have nearest neighbors of A and B. So that's the energy of it. Sorry, I should have emphasized one point, that the energy is only one component of the way you get this phase diagram is you minimize not the energy but the free energy. Okay, and the relevant free energy in this ensemble is the Gibbs free energy, which is E minus Ts plus Hm or minus Hm, where M is the magnetization. Okay, so one way of lowering the free energy is by reducing the energy. Another way of lowering the free energy is by increasing the entropy, right? Because you have a minus sign sitting out there. So the sort of physical principle that governs your preferred state is what minimizes the free energy. At high temperatures, this factor wins out. You have a high entropy disordered state with many configurations, and at low temperature, this factor wins out, and you have an aligned phase where the energies are minimized. Okay, and that's again similarly in the binary alloy. At high temperatures, you expect to have a disordered phase where A and B are randomly mixed, and at low temperatures, you have a ordered phase where A and B phase separate out. So again, let me draw the phase diagram of which you get from the Ising model. So this phase diagram is the same as this phase diagram, but it's plotted in a slightly different ensemble. Let me sort of say what I mean. So this phase diagram was worked out in an ensemble of fixed T, H, and N, where N is the total number. I had 1 mole of spins. Okay, This particular phase diagram is usually worked out in an ensemble at fixed T, magnetization and N. Okay. So the appropriate free energy so the magnetization is fixed for the following reason, that sum over Si is just equal to the number of A atoms minus the number of B atoms, and that's fixed for a given binary mixture basically, right? So though it's the same phase diagram, it's going to look a bit different, and I hope you students are aware that you can work out the phase diagram of the magnet in either an ensemble with T fixed or S fixed, its conjugate entropy, H fixed or M fixed, its conjugate, and N fixed or mu fixed, its conjugate. So that gives you actually 8 possible ensembles, and these are just 2 of the ensembles. So maybe as a homework problem, you go work out the phase diagram in all other ensembles in mean field theory. Okay, that's a good sort of this thing problem to do. But anyway, the phase diagram that emerges is again looks like the following. So now you have the fraction of A on the x-axis, and that determines the magnetization. As I told you, this is a fixed magnetization ensemble. The magnetization, I should put the magnetization in quotes, because it's a pseudo magnetization. There are no real spins or magnets or magnetization out here. The fraction of A ranges from 0, which is no oil, let's say A is oil, to 1, which is all oil. Okay. Correspondingly, the fraction of water, so if it's an oil and water mixture, ranges from 1 at this end to 0 at this end. Okay. And then you have this sort of famous coexistence curve, which you first encounter when you do the van der Waals equation of state. And then you have a critical point, and in this symmetric Ising model, the critical point is sitting at, the coordinates of the critical point are Ca critical is equal to half, corresponding to a 50-50 concentration, and then there's a Tc, which is the critical temperature basically. Okay, and here you have at high temperatures entropy wins out, you have the homogeneous phase. At low temperatures energy wins out, and you have a segregated state. And there's all sorts of things like the lever rule and this and that. I'm not going to go into those. I can answer questions if you have, because that's not the main subject of the talk. And people often talk, and this is a very controversial and still open point, about whether there is another dashed line out there, which is usually known as the spinodal boundary. Okay. And many colleagues, I'm sure Pinaki will tell you all about the spinodal boundary, because he uses it in his research, encounter this spinodal boundary, and whether it actually exists or doesn't exist, or is it a mean field artifact, or so on and so forth. Okay, but let's not get into that. So again, around the critical point, you have critical phenomena, and there's been a huge amount of interest in critical phenomena. And again, it's understood in terms of the same physics as what was understood with at that critical point. And if you want to sort of see this phase diagram equivalent to that, basically what happens is the following. You rotate it by 90 degrees, so the temperature becomes a y-axis, and this coexistence line opens up in this case into a coexistence curve, basically. And the physics problem in the kinetics is the following. You start off at the homogeneous high temperature phase. Oil and water are homogeneously mixed. So you start off at high temperature, let's say T greater than Tc, rapidly quench the system down below the critical temperature. The system can't live in this gap. It phase separates into one constituent, which is that composition, and one constituent that is that composition. Okay, and this is my second paradigm of non-equilibrium physics or kinetics of phase transitions. what is the dynamics whereby I get from the initially homogeneous state to the final phase separated state. Okay, so that's the next sort of paradigmatic question. And what else do I want to say? There's issues about nucleation and stuff like that, which we'll get into later. For the moment, let's just consider a quench below these dashed lines where you spontaneously phase separate into your preferred equilibrium phase, basically. Okay, so this is a problem of non-conserved order parameter. Because the magnetization is the order parameter of the system, and the magnetization sort of finally converts to all plus or all minus, and this is called a problem with conserved order parameter. And the conserved order parameter problem is substantially harder than the non-conserved problem. We have a pretty good understanding of that in the kinetics of phase transitions, but there are still many open questions on that, even though that's a 50-year-old plus problem, basically. Okay, so are there any questions at this point, or can I show some? I think I should show you some pictures before we sort of move on of the typical evolution that you expect. Are there any doubts at this point? Huh? This is all straightforward enough, I suppose. Huh? Remember, I'm primarily a teacher, and no doubt is, I mean, if you have a doubt, likely 4 other people have the same doubt. So no doubt is silly or whatever. Just ask your question. Okay? Yes, yes.
What does it mean by non-conserved order parameter and conserved order parameter?
I will show you when I show you the evolution snapshot. Just give me 2 minutes. Basically, the order parameter that describes the system is the magnetization. You start off from a paramagnetic state where magnetization is 0, and then you go into a final state where all spins are pointing up or down on the average. So you go to a non-zero magnetization at the end. Hence, there's no conservation law. In this case, though you phase separate, you still have to maintain the same number of oil atoms and water atoms, or water molecules, right? That's the conservation constraint, and that actually makes this problem way harder to solve. And it's still, in terms of the kinetics of phase transitions, this is an open problem. Okay. We'll get into this more. Huh? Any other questions? Huh? Yes, please.
The Ising model, if we change the x symbol to T, capital F, that means the same x symbol as the primary and the phase pair completely the same.
No. This is in the TMN ensemble. So this is worked out in the TMN ensemble. I claim that with a little imagination, it's the same as this phase diagram. You rotate this by 90 degrees. Then if you fix the conjugate of H, this first order line opens out into a coexistence region. Okay? And the coexistence region means you can't live in there. If somehow you force the system to come down here, it's got to phase separate into constituents which are rich in that composition and rich in that composition. Gibbs already knew this. I think this is called the Gibbs-Lever rule. Okay, so it's the same phase diagram, but just worked out in a different ensemble. And as a matter of fact, these are just 2 ensembles. You can actually, there's 6 more ensembles. Well, a couple of them are trivial, but I think it's a good exercise. I normally give this to my MSc students to work out the different free energies in all the ensembles and figure out the phase diagram in all the ensembles. Okay? Okay. So, yeah. Any other questions? Yeah, please. There is difference. In the simplest version of the problem, you look at quenches, which are instantaneous sort of. I mean, you might ask, if I take a tray of ice out of the freezer, how do I know that the core of the ice is at the same temperature as the surface of the ice? And that's a very good question, okay? So there's conduction and all that involved. But in the 0th version of the problem, which is already going to be pretty difficult, you look at how the sort of, at an instantaneous quench, okay? time dependent quenches are very important in a host of situations, and though this is way ahead of where we are right now, there's this well known, Kibble has a double B, Kibble-Zurich mechanism. And Kibble and Zurich, I think, well, Kibble is of course a well-known guy in particle physics, and so is Zurich for that matter. So they had the question, what does the density of defects depend, how does it depend on the time the quench takes and the quench protocol? Okay. And that's very important, because in the early universe, if you're looking at it as a kinetic phenomenon, you're interested what sort of density of defects the early universe had and how the quench took place and so on and so forth. Okay. So for the moment, let's just do what the metallurgists and the material scientists do. Let's just take it as an instantaneous quench. In the Kibble-Zurich language, if the time scale of the quench is 0, which means it's instantaneous, then the initial density of defects in the system is infinite. Okay. Okay, can I just request somebody to help me out with this? I want to show you some pictures, but I need my sort of PowerPoint. Yeah. Okay, at a first order boundary, you have a discontinuity in the first derivative of the appropriate free energy. So the free energy is continuous, but you have a discontinuity in the first derivative, and that's like latent heat is an entropy discontinuity, or the volume is a discontinuity, specific volume. And at the second order phase transition, which is usually called a weaker phase transition, you have the free energy continuous, you have the first derivative continuous, the second derivative has a discontinuity. And those are quantities which are harder to measure, like the susceptibility and the specific heat and so on and so forth. Right? This is this is called the Ehrenfest classification, and nature mostly gives us first and second order phase transitions. There are very few examples of third order phase transitions, but I think none higher than that, unless in some way the so-called Kosterlitz-Thouless transition you can think of as an infinite order phase transition, but there are arguments about that. Sorry? But I can't hear you clearly, sorry.
Ice, that's a third order or second order?
Which one? Ice.
Water to ice.
Yeah, so that's exactly the point of the phase diagram I showed you. You can go from water to ice through maybe I'll just show you the phase diagram. That will be easier to sort of, but.
I think you can just.
Yeah, maybe just sit here.
Yeah, I think this is easier.
Okay, let's just do that. Okay, so yeah, okay, so that's a schematic phase diagram of a fluid basically. Okay, that's your phase diagram of water, and so the experimentalist plots it in the temperature, pressure, and let's say you are the third axis is a mole of water molecules. Okay, so that's fixed. Okay, and you can sit anywhere in the phase diagram that you want to. Basically, so you can sit anywhere in the phase diagram that you want to, and the appropriate state is the one that minimizes the appropriate free energy. The appropriate free energy in this case is the Gibbs free energy. Basically, it's internal energy and entropy. That's the usual trade-off. Okay, so if you're at low temperatures and high pressures, then energy wins out. Energetically, water wants to be a solid, a crystal. Okay. At high temperatures and low pressures, entropy wins out and you want to be a gas. And at moderate temperatures and moderate pressures, well, you have a liquid phase basically. Okay. So now you can go from, your question was how do you go from liquid to solid? You can go through this boundary, which is a first order boundary, which means if the experimentalist does some trajectory like that, she's going to see a discontinuity in the first derivative. Okay. But on the other hand, if you go from liquid to gas, again you can go through this first order boundary. You see a discontinuity in the first derivative. But if you choose a protocol that takes you through the critical point, then you see a second order discontinuity. Okay? And if you take a protocol that avoids the critical point altogether, then you don't see any discontinuity in any derivatives whatsoever. Yeah, these are basic concepts we should get clear before we go on, huh? Is it clear now? So both first and second order phase transitions exist out here. Okay. The kinetics problem I talked about, the kinetics problem, the first one about the tray of ice is, say you have the water sitting in the freezer, so that's ice, and then you rapidly bring it to room temperature, so it would like to be liquid. What is the dynamics whereby the solid converts to the liquid phase? Okay. Just one minute. Supersaturated vapor is gas sitting on the wrong side of the gas liquid boundary, which means it would like to be a liquid, but it needs a nucleation or a kick. It's stuck in what's called a metastable state, and that nucleation is what enables, so thermodynamically it wants to be water, but it needs to be kicked over a barrier before it can become water. So that's the second example, the supersaturated cloud converting to rain. No, so there's a critical point here. That one. That's what I said. If the experimentalist takes a protocol, she's doing this experiment in a lab, right? These are all experimental statements. The Ising model, etc., came later. If she takes a trajectory through that point precisely, then she sees the free energy is continuous, the first derivative is continuous, the second derivative is discontinuous. One of the second derivatives at least, or more. Okay. On the other hand, if she takes a trajectory from here, then she sees a discontinuity in the first derivative. If she takes a trajectory through here, she sees no discontinuity whatsoever. The phase diagram of the fluid is sort of reasonably clear. Okay, I mean, you can, as I said, we can just discuss this, and there's no problem at all. Okay, so now this is the phase diagram of the magnet, which I've sort of shown for you. It's plotted in the temperature magnetic field number ensemble. The number is just the third axis, which is fixed at 1 mole. And the experiment I'm doing now, this is a kinetics experiment, is I start out there and quench rapidly down there. Okay. Now the system wants to be ferromagnet, but it's happy being up ferromagnet or down ferromagnet. It doesn't care about which one it is. So that's the non-equilibrium evolution that I'm going to show you. At time t, so that's the time on the snapshots. At time t equal to 0, somewhere out here, you have a disordered mix of up and down spins. That's your paramagnet. Okay. As time goes on, the phase transition starts. It doesn't happen instantaneously, of course, right? So you develop domains of up spins and which are the black regions, and domains of down spins, which are the white regions. Okay. And it's equally happy to be either of them. These domains grow. That's the process I want to get a handle on, how they grow. And they grow, and they grow, and they grow, and then in the final snapshot, which I have not shown to you, you'll either go all black or all white. If you do the experiments 100 times, you'll go all black, maybe 40, 50 times, and all white 50 times. Huh? So that's the kinetics, and this is a non-equilibrium process which we have not been able to solve analytically so far. Okay, I mean, we've not even been able to solve the Ising model analytically, leave alone the kinetic Ising model. Okay, so I want to get a grip on what this dynamics is. Staring at the pictures, it's sort of obvious what the questions in your mind would be. There's a characteristic domain length scale. How does that grow with time? Okay, and then there's some morphology, which is usually measured by some correlation function or structure factor. How does that change with time? And now one's looking at, again I emphasize, a non-equilibrium problem which is analytically not tractable. Okay. So you have to, but again, that doesn't deter us as theorists. As theorists, we try to sort of figure out approximate ways to solve the problem, exactly as we did in the static phase diagram. We couldn't solve the Ising model, but we found a pretty good approximation via mean field theory. So the same thing we'll do out here. Okay, so that's the ordering ferromagnet. Now the second problem, the phase separating binary mixture. So let's forget about the superconductor. I'll talk about that later. So this is the phase diagram of the binary mixture. You can have an oil-water mixture, you can have a polymer blend, you can have a binary alloy, you can have a bunch of boys and girls. You can imagine even in social physics or econophysics, there are many binary mixtures, right? The phase diagram is the following. That's the fraction of oil. That's the temperature. At high temperatures, you have a homogeneous phase, entropy wins out. You rapidly quench into the segregated phase and ask how you evolve to the phase separated phase. Okay. So, that is the next slide that I am going to show you, and that is the evolution of the kinetics of phase separation. Okay. So, maybe I should just sort of go back for a minute because I should give a little bit away already. As I said, we can't solve this analytically. What we can do is we can approximately capture the dynamics in terms of what the defects are doing. The defects are the boundaries between up and down spins. See, in the up domains you are equilibrated, in the down domains you are equilibrated. All the non-equilibrium stuff is happening in the interface. Okay? And you can use these interfaces or kinks or domain walls or whatever your favorite grain boundaries, favorite nomenclature is, to capture the dynamics. And that's what we're going to try to do later if I get to that point basically. Okay? But basically you can think of these boundaries doing random walks, and that's it. They're just local random walks, there's no conservation law. Okay. Now you look at the phase separation problem. I'll also tell you why it's harder. At t equal to, so this is a 50-50 mixture of oil and water. You start off at time t equal to 0 with a homogeneous mixture of oil and water, black and white. You develop domains which are rich in oil, that's the black domains, and domains which are rich in water, which are the white domains. Okay? Obviously, as this time goes on, the domains grow. But you need both black and white domains because you have 50% black and white here, you have 50% black and white here, and as a matter of fact, that conservation constraint must be respected for all times. Okay? So, you have no option but to sort of respect it. So, you continue this tortuous problem of domain growth and grow, and finally at time t equal to infinity, when your phase transition is complete, you have a big blob of oil and a big blob of water, phase separated. If you start off with a 30-70 mixture, I'll show you that picture also next. But basically, so again there are interfaces out here, there are defects out here, but the dynamics is much more complicated. The dynamics is correlated. If an interface wiggles somewhere, all other interfaces must readjust to conserve the order parameter. Hellishly difficult problem, which is not proven tractable so far. Okay? That's the sort of point I want to make. And as a matter of fact, the only limit it's been understood in is this first classic paper by Lifshitz and Sliozov. Lifshitz is a very well-known name in statistics. There are actually two Lifshitz, by the way. And they also wrote books with Landau. Some of the Landau books are written with Lifshitz. So Lifshitz actually solved this problem in the limit where you have a vanishingly small fraction of one of the components. Okay? But this 50-50 mix or slightly asymmetric mix has not yet been solved. Okay? Because of this correlated motion of the interfaces. Okay? That's an asymmetric mix, 30% oil and water. You start off with a homogeneous mix of oil and water, 30% oil, 70% water. Droplets of oil grow in the majority of water. The droplets coarsen. The physics is that the small droplets get eaten by the larger droplets, right? Because the chemical potential is smaller on the surfaces of the larger droplets. Okay? So, this happens in real life also, right? Small companies get eaten up by large companies. Or small countries nowadays get eaten up by large countries, right? Unfortunately. Okay. So, the droplets continue to grow. Again, it's the same painful process where you have to conserve the composition for all times and grow. And finally, at time t equal to infinity, you have a phase separation is complete, but you have one large droplet of oil sitting in a matrix of water. This is called by the metallurgists as Ostwald ripening. Of course, you guys are all theorists, right? So, but sort of people who do nanophysics and all that often see this phenomenon of Ostwald ripening. Well, not just nanophysics, all material scientists encounter this at one stage or the other. Okay. Again, this is a hellishly difficult problem because I have a conservation law. If one droplet vanishes, it can't just vanish by doing a random walk. The material has to evaporate. The material on the smaller droplet has to evaporate, transport through water and go deposit on a larger droplet elsewhere. It's a conserved quantity. Okay. Much harder problem. In the ferromagnet, the interface just sort of wiggles locally and is happy doing that basically. Okay. Finally, the droplet just disappears or becomes larger. Okay. So, these are the kinetics problems we are going to target. We've sort of diverted a little bit, but it was important to show you these figures. Huh? Is there any question at this point? Yes, please. Betty, you have to speak up. I'm really old now. Kuch sunai nahi deta. No. In this conserved problem, at the end of the day, you'll have the same composition you started with. And at every intermediate process, you'll have the same composition. That's the conservation law.
And it's like taking small drops are coming together.
Yeah, well, what's happening actually is that the small droplets have higher chemical potential on their interfaces. They're evaporating and getting eaten by the larger droplets. The larger droplets in turn are being eaten by larger droplets. And at the end of the day, you still have to maintain that 30%, 70% mix. So at the end of the day, you have a 30% oil droplet suspended in a background of 70% water, basically. Okay.
Sir, if you increase the quench,
Yeah.
what will happen there? I mean, quasi-statically, if you induce the quench. So, just one like that is
If you do a time dependent quench, slow quench. No, that's an important experiment. As I said, that's people do that also. It's not going to change the dynamics of the phase transition. What it will change is the initial density of defects. In my sort of snapshots out here, if you quench from the paramagnetic phase, the initial phase is the paramagnetic phase, right? So that's another way of thinking of the paramagnetic phase is as a mixture of infinite up and down domains. So you have an infinite density of defects. Similarly, if you quench from an oil-water mixture, homogeneous phase where oil is sitting next to water, another way of interpreting it is an infinite density of defects in the oil and water mixture. Okay. So in that language, a instantaneous quench gives you infinite density of defects, and then it evolves as so. And a finite time quench gives you a different density of defects, but the evolution is still the same. The late stages are the same. Okay. Okay, there was another question. Yeah. Huh?
critical slowdown.
Yeah, at critical slowing down is another issue. Here you always quench far from the critical point. Critical slowing down occurs when you are at the critical point and you're looking at dynamics out there. At dynamics in the equilibrium state. This is, so you're still close to equilibrium. And you have all these, I don't know, whether you work on that, you have all these model A, model B, etc. of Halperin and Hohenberg, which are very sort of commonly used. Okay. Here, this is a far from equilibrium problem. You have these nonlinear kink structures forming between phases, and they are evolving. So you don't have to worry about critical slowing down, basically. Okay, there was a couple more questions. Yeah.
Temperature we are observing is the critical temperature. At the critical temperature we are observing
No, but yeah, we have quenched. Oops, how do I go up? Yeah. We have quenched. Let me just sort of. We have quenched from up here to down here. So we are not at the critical temperature. We are far from the critical temperature. At the critical temperature, you would see critical slowing down and other physics also. Okay. So the standard phase ordering or the kinetics of phase transitions problem is you quench from high temperature to low temperature, and you avoid the critical point to avoid any complications of the critical point. Okay. Yeah. Does that answer your question? Yeah. So you're not at the critical temperature. That's the answer. Yeah.
the oil gas mixture, so when the small droplet actually forms, so how they actually sense there is some big droplet around and then diffuse and then
So, as I said, the global principle is the following, that at this, okay, maybe I go to the picture of the droplets. In your initial condition, you are high on free energy. At the low temperature, you can do better free energetically. You can lower your free energy. So, the path is one of minimization of the free energy. That's a sort of global principle that the system, I mean all systems in nature do this, proteins do it, glasses do it. The system will try to find its minimum of the free energy. And at the low temperature, the minimum is the phase separated state basically. What is the drive? There are very little sort of modulations of the density in these seemingly bulk regions, and those drive the transport. Okay. So, it is not that the black regions are absolutely oil, perfect oil, and the white regions are absolutely oil, they are water, they have little fluctuations, small amplitude fluctuations, and those drive the transport, if you are looking at the mechanistics of it. Okay. Okay, any other questions? Yes.
will they have blocks coming out or say like a system spanning network type of mesh will depend on the ratio of these components.
Yeah, so when you have 50-50, you get a bicontinuous structure in 2D. That's the percolation sort of threshold, right? Huh? But here, obviously, you can't get a percolating cluster, huh? As opposed to whether you'll have a round blob or a elongated blob. You tell me. What do you make a guess? It has to do with surface tension. So, the kinks cost me, the boundaries cost me surface tension. I am trying to get rid of the surface tension, reduce the surface tension. So, now tell me what's the answer? Exactly, because that minimizes the surface area and that gives me the minimum surface tension. Okay. So, if you see droplets, of course, droplets falling from the sky are usually a little elongated, but that is because there is gravity in there also. Here there is no gravity in these snapshots. Okay. Okay. Any other questions?
Can I host?
Of course, please. No.
So just if I just look at a situation which is sort of normal in metallurgy, or when you form solids,
Yeah.
ordered solids,
Yeah.
from high temperature mesh which is disordered.
Yeah. You form some sort of order disorder transition kind of thing.
AB alloy or
Yeah.
B alloy.
Right. Yeah. That's right. Yeah.
You don't require Na equal to Nb.
That's right. Yeah. Well, Na is equal to Nb, but the order parameter is not conserved in that case.
Two types of Na, 2 times Na and 1 Nb.
Exactly. But here also you can have 2 times Na and 1 Nb. Yeah, but you form a, yeah, okay, sorry, but go ahead, I should not interrupt your question, yeah.
So I mean, if my low temperature state is ordered, not phase separated, meaning if S of k has a maximum at some k which is corresponds to the ordering wave vector, then if I think about a quench, a sudden quench or a rapid quench,
Yeah.
how should I think about it?
Okay, that's actually a very good question, and I'm glad you brought it up, because this, my claim, and I hope to demonstrate this later, is that the situation you have is that of an anti-ferromagnet, and that's actually equivalent to the ferromagnet. All you have to do is change the order parameter from the usual magnetization to what's called the staggered magnetization, because in the simplest case of an AB disorder transition, you form alternating structures of A, B, A, B, A, B, or BA, BA, BA. And then of course you can have, if you have a 25-75 composition, you can have BCC, not BCC, you can have some whatever, various sort of, all of those are non-conserved transitions, because the entire system will finally be tiled by let us say the AB phase, and the boundaries in that case, the domain boundaries will be where AB switches to BA. That is your defect, and ultimately the system gets rid of all those defects in annealing. So, it is the nomenclature, that is a much less studied problem by the way, but the nomenclature people use is that is a that is a weak conservation law. The order parameter is not conserved, but there's a slow variable which is a density which is conserved. And yeah, I don't know whether you're familiar. There's this famous article of Hohenberg and Halperin. Have any of the students seen it in Rev Mod Physics? It's one of the classics. It describes the models of dynamical critical phenomena. So that's dynamics at the critical point. I should write the name down. This is a famous article by Hohenberg and Halperin. Two very famous names in statistical physics, guys, for the students. Okay, so in the Hohenberg-Halperin model, the non-conserved problem is known. They give these very dull names. It's called Model A. Okay, the conserved problem phase separation is Model B in their language. Okay, and the problem you're talking about is Model C. Model C means the primary order parameter is non-conserved, but there's an auxiliary order parameter, the density field, which is conserved. So that's this coupled differential equations written down by Hohenberg and Halperin. I don't remember the reference of this, but you can very easily find it. It was in Reviews of Modern Physics, I think in 1977 or something. Okay. And for those of you who want to learn critical dynamics and far from equilibrium dynamics, that's a good paper to look at, yeah. Very compact, but it's a good paper. Another good place is this book by a gentleman called Shankeng Ma, S.K. Ma. I think it's called Modern Theory of Critical Phenomena or something. Okay. Sorry, have I answered all questions now? We still have 20 minutes left of the talk? Okay. Please ask questions. Yeah, I'm very happy.
So, if you go to this oil and is there a possibility that if you're at very dilute fraction, you make like a Wigner crystal on the back?
Oh, absolutely. So, these are the simplest version of the.
So it doesn't necessarily have to phase separate.
It doesn't have to phase separate. You can settle down into what's called microphase separation, where you have a phase separated state up to a certain point. And a lot of active materials, they don't show full phase separation, they show active. I mean, I can give you a very sort of straightforward example which engineers worry about a lot. You don't need to go to a quantum mechanical system and get a Wigner crystal. If you have a block copolymer is where you have a polymer jointed to a B polymer, and A and B dislike each other. So they like to phase separate, but because obviously of that topological connection, they can only phase separate up to a certain point. So they usually fall lamellar structures and things like that. Those are called block copolymer systems. Okay, and that's an example of where you have microphase separation, basically. So I'm just sort of discussing the simplest problems which are already interesting enough. Okay, move on. Okay, so now that we are clear on the physics problems we want to solve, let's sort of actually start introducing some framework in which we study them, okay? And I'm going to get rid of this. So maybe I'll leave this phase diagram up here because that's important. Okay, so the first problem I'm going to consider, so this is now section 2 of my lectures, is on Glauber kinetics. Glauber kinetics is what describes the ordering which now we know to be non-conserved of a ferromagnet. Again, that's a name that I use, but it applies to a vast variety of different systems, basically. Okay. So what is Glauber kinetics? Glauber kinetics is, see, if you try to write down dynamics of these Ising models, you actually immediately find that there's no dynamics because the Poisson bracket of the spin variables are basically classical objects and they don't have any intrinsic dynamics of their own. So what you do is the following, the sort of way people get around this is the following, and this is sort of the basis of any Monte Carlo simulation. you randomly pick spins Si and flip them to minus Si. Okay? So you take the spin at one point and just flip it randomly and this flip is sort of generated by immersing it in some kind of bath or reservoir which drives a stochastic kinetics into it. So actually you can calculate, I think the first person to do calculations of a bath coupled to a system was Zwanzig, and then later on also there's a very famous paper by Leggett and Caldera and so on and so forth. Okay, so of course I'm not going to go into these models where they couple a sort of Ising spin model with a bath of harmonic oscillators. I'm just going to take the basic Glauber kinetics problem, and the basic Glauber kinetics problem is the following. He says that the net sum total of this bath is to drive stochastic spin flips into the system. And those of you who've done Monte Carlo simulations would have been told to either do Glauber kinetics or Kawasaki kinetics, I presume. Okay, so that's yeah. Just a piece of trivia. Glauber is actually let me put this correctly. Glauber is a Nobel laureate, by the way, not for inventing Glauber kinetics. He was given the Nobel Prize for this quantum optics, nonlinear quantum optics theory. And there was some issue with the person whom this, I mean, many in India felt that the person whom this hall is named after should have been the correct recipient of the Nobel Prize. But anyway, Glauber got it, and that's that, I guess. Yeah. Okay, but that happens, I suppose. Okay, so you have this spin flip kinetics. So maybe I'll just call it spin flip kinetics. And immediately you can see that this spin flip kinetics does not conserve the order parameter. It takes a spin and puts it to down. Okay. Later on I'll introduce Kawasaki kinetics. In Kawasaki spin exchange kinetics, you take two neighboring spins randomly and interchange them basically. Okay. So that obviously conserves the composition of up spins and down spins, and that's a conservation of the order parameter. Okay. But the first thing, so you have this Glauber kinetics. And I don't know how familiar you guys are with this formalism, but basically if you have a phase space of spin variables Si, so it's kind of unlike your a gas, a fluid phase state, it's not a continuous phase state, it's just it's got if you have n spins, this state consists of 2 raised to power n states. This phase consists of 2 raised to power n state, and you have some probability distribution of the spin configurations on this lattice. Remember, we are looking at a non-equilibrium problem. So let's write down the evolution of the probability distribution. This is a standard tool of non-equilibrium stat mech called a master equation. Have people used the master equation before? Huh? Okay, so let me write down the master equation for this evolution. So basically, let's say I have some spin state Si, and I have to worry about whether the spin flips take me out of that state or spin flips in neighboring configurations bring me into that state. So let's without further ado write the master equation, and then we'll try to actually derive a partial differential equation which describes non-conserved ordering dynamics. So the master equation is the following: that the rate of change of probability of Si, a certain configuration, at time t, because it's a non-equilibrium problem, in equilibrium the time dependence goes away, that's equal to first loss term where I randomly pick any spin I and look at the probability of W, that's the probability of Si flipping to minus Si, okay. And then I have the probability of Si t. So that's what I call the loss term. If I have a configuration sitting there, how many ways can I lose that configuration? And obviously by Glauber kinetics I can do it by randomly picking one spin and flipping it, and I can pick any one of those spins. So I sum I from 1 to n. So this is the loss term in the master equation. All master equations, by the way, have loss terms and they have gain terms. What is the gain term? That's obviously going to come with a plus sign. So that is now from nearby configurations which differ slightly from this configuration by a single spin. If you flip that single spin, then you will come into this configuration. That ensemble is going to come into that configuration. So you are looking here at the transition probability of minus Si flipping to plus Si, and the probability distribution of a configuration where all spins are the same as my desired configuration, except for the ith spin which is minus Si, and all other spins are the same at time t. That is the master equation, and that is the gain term. So, I am going to put this in a box because we will encounter, we are going to make use of this master equation to derive equations for phase ordering. So, what I got targeted for this course is basically the following. I am going to help, we are going to derive this equation, and we are going to use the equation that we get, which is called the time dependent Ginzburg-Landau equation, to make statements about analytic statements about the phase ordering process. Okay, and I again remind you that we can't analytically solve the time dependent Ginzburg-Landau equation. So we will use the interfaces or the defects to capture the dynamics of the ordering ferromagnet. Okay, is the master equation clear to everybody? Yeah.
Just to emphasize that the one in the curly bracket
Yeah.
is basically the configuration.
Yeah.
And then the one which is written SI is basically the single scheme. So
No. So,
one in the transition.
yeah. Oh, so I should have said that. Yeah. So this curly bracket SI denotes the configuration of all the spins, and whenever I talk about SI, I'm glad Arnab said that. Whenever I talk of just SI without curly brackets, I'm referring to a specific spin. So I mean, I usually find, that's what I tell my students, it's better to read this conceptually and then translate it to mathematics. So conceptually, all I'm saying is the following: the number of ensembles having that state changes as follows. Either you can have that state and flip away from it, or you can be in a nearby state with one spin different and flip into it. So that's the gain and the loss term, and all master equations actually go like that. Okay, we have till about 1.
Yes, you can, if you are okay with it.
I want to now do some calculations with this. I'm wondering whether we should
Or otherwise we can resume at 250.
215 or okay. That might be better, right? Because I want to do some calculations with this master equation.
Maybe it is, we can start from 250.
Okay. Any doubts at this point? The physics problem that we're talking about is clear?
Can you explain master equation once again?
Okay. The master, so that's your phase space, right? The phase space for this Ising model consists of a collection of spins SI, all have configurations +1 or -1. +1 is a spin pointing in the up direction, -1 is a spin pointing in the down direction. Simplest possible model. Okay. Now I have a time dependent probability distribution of the states because it's a non-equilibrium problem. Okay. So I start off from a disordered state, and the disordered state P as a function of SI at time t equal to 0 corresponds to some disordered initial condition basically, right, which means that you randomly pick each spin to be up or down as you do in a Monte Carlo simulation. Now this configuration evolves. So what is the evolution? If you're asking the probability of a certain state in phase space, you have a probability of escaping from it. So if you have the probability of a certain state, multiplied by the probability of escaping from it, that subtracts from this probability. So that's the minus sign. Or you have a nearby state which differs from this state only by one spin being flipped. Okay? Then from that state I can come here by reflipping that spin again, so that now I have exactly the same configuration. Okay? So that's the second term. I look at the probability of a nearby configuration where all spins are the same as this, except for the ith spin which has a minus sign, and then I look at the probability of flipping minus Si to plus Si. Okay? And this is going to be the basis of my calculation from now. Obviously, the most important sort of thing out here is the choice of W. Okay? And there's a little physics in that. Your choice of W in a Monte Carlo simulation sort of must obey what's called a detailed balance condition. I guess you guys have heard about all this, right? Huh? So, to drive the system to equilibrium, you need to obey a detailed balance condition. Okay? At the end of the day, maybe I can just spell out a little bit of the path ahead. I am going to sort of find the evolution of this average spin, which is now space dependent. I have a domain growth process, so it's space dependent. And then I am going to try to approximately solve it as I solved using the kinks as my tools of solution, basically. Okay, any other questions? So then, yeah.
You said W is like probability, but it's more like rates.
A rate, it's the same thing, yeah. You can call it a rate if you prefer. Okay. It's a rate of transition from Si to minus Si. You pick a single spin and you flip it, and you are allowed to pick any of those n spins as your single spin. That's again, like I said, it's based on a Monte Carlo simulation. You randomly pick a spin and flip it and see what happens. Do you, which direction? Have you all done Monte Carlo simulations? Metropolis and all that, huh? I presume, right? Yeah. Okay, anyway. That's the basically a Monte Carlo simulation with Glauber kinetics written down in the form of a mass equation.
The argument in the second term, probably.
Yeah. So
Can you explain the argument, like the coefficient that
this configuration is identical to that one, except for the ith spin, which is minus Si rather than plus Si. So this I call a nearby configuration. It's something that is nearby in state space to that. Huh? And this can become this configuration by picking minus Si and flipping it to plus Si. So that's the rate of flipping minus Si to plus Si. Okay. Yeah.
So in this W, is it dependent upon I? Will it depend upon the environment, the rest of the state around it, or will it be independent of?
Okay, that's a very good question. Actually, in the simplest case, it just depends on the energy change involved in the flip. In what's called Metropolis Monte Carlo, it depends on the energy change that's involved. So it's independent of I.
It's independent of I, but it depends on the local configuration.
Exactly, exactly. So because the delta H, the delta change of energy, depends on the local configuration, basically. Yeah. Huh?
Put the W A side to minus A side and minus side A side. The W's are same, right?
Yeah, you have the same expression for the transition probability, and that's what I'm going to write down next. You need a transition probability which obeys what's called detailed balance condition. Okay. So the expressions for W are the same, but obviously the energy involved in this flip is different from the energy involved in this flip. Actually, more accurately, the energy involved in this flip is minus the energy involved in that flip, basically. Okay. And you'll have to compute the energy which is involved in this flip, starting from the Ising model, which I'll do after the break. Okay. Any other doubts? Okay, so we proceed after lunch. Yeah.